Hello guys, welcome back to your favorite and India's most affordable learning platform, Physics Wallah. So in the last session we have completed the motion in a plane chapter, right? So where in motion in a plane we have covered from basics, that is vectors, so and then till the projectile motion on an inclined plane. So every topic we covered. So just you guys have to revise the topics and do the questions related to that. Okay, so that's very important. So today we are going to start one interesting chapter, that is laws of motion, Newton laws of motion, where we'll study the first law of motion, second law of motion and third law of motion, and then we'll also study friction in this chapter itself. So I'm going to allot 7 to 8 lectures depending on the duration. So mostly 7 lectures I'll try to complete. So if not possible, I'll take the 8th lecture as well for this chapter. Okay, so this chapter is very important for the other chapters as well, because wherever you have to draw the free body diagram, so the laws of motion plays a crucial role. Okay, so in every other chapters of physics, so we have to understand what is the force acting on the body and what is the free body diagram of that particular situation given. So all these things will be related to this chapter only. Okay, so that's why we are going to discuss this chapter in detail with lots of numericals. Okay, so and I am recommending you to do extra questions also apart from the questions which I am solving in the class. So you have to do some extra questions, whether it's your reference book or previous year questions or some other book, so whatever it is, but you have to solve the questions related to these topics. Okay, chalo. So today's agenda is, first we'll understand the basics, so the types of forces, and then we'll understand what is free body diagram. Okay, so then we'll see the first law, Newton's first law of motion. So the Newton's first law of motion. Okay, so let it be. So the free body diagram means, after that we'll understand equilibrium and Newton's first law of motion. Okay, chalo. So first let's start with the basics. You already know there are two types of forces that exist. So one is the contact force, the other one is the non-contact forces, right? So under the contact forces we have 4 forces. What are they? Normal reaction, tension force, spring force, friction force. So just the theory part, listen carefully guys. Okay, so numericals will come. So once we understand the basics, we'll go step by step. Okay, chal. So the contact forces, the normal reaction we are going to study in today's session itself. Okay, whereas the next the next tension force we'll study today itself, this one also, and then so the spring force we'll study it in the SHM. So in this chapter also we'll study, so in the SHM also we'll study in detail. So SHM and NLM, Newton laws of motion. And then friction force, so the last topic of this chapter is going to be friction. So where in this chapter only we'll cover, so that is 6, 7, 8 lectures mostly I'll allot to friction force. Okay, and then coming to the non-contact forces in our syllabus, we have the gravitational force, so which we'll study it as a separate chapter, which is gravitation, so which I am going to teach after work energy power. So we'll study the gravitation, right? So then the electrostatic force, so this you will study in the class 12th, the first topic of class 12, that is electrostatics, where 2 chapters will be there in the electrostatics. So first one is the electric charges and fields, then electric potential and capacitance. So there you'll understand the electrostatic force. So then the magnetic force, so this is also in second year, that is +2, so which is a magnetic force. So magnetism I can write, in the magnetism topic we'll study this. Okay, clear? These are the forces which we study in our total +1 and +2. Understood? So these forces we'll study in this chapter itself. So these all forces. Okay, so and another common force is a weight. So weight is also a type of force. Let's suppose we are standing here, so that the weight, our weight, which is a force acting on us. Understanding? Clear? So just understand the weight. Let's understand the weight in detail. See here, the weight of the object is equal to the gravitational force with which it pulls downward. So the gravitational force with which the each pulls it downward. So which is nothing but simply, so let's suppose this is the ground. So you kept a body of mass m here. So then what is the weight acting on it? So it's mass times the gravitational force. Mass times the gravitational force. Yes or no? So this thing you already know. So whenever a body is placed like this, okay, so this is of body of mass m. So then the weight of the body is going to be mg is the weight. M is the mass. Okay, so there is a difference between weight and mass, right? So m is the mass, whereas weight of the body is mg. Mass multiplied by gravitational force, so which gives a mg. So the weight is not always equals to mg, guys. So weight, this point is important. So the weight is not always equal to mg. So this scenario, let's understand. I'll draw it in this new slide. See here. So let's consider we have a body of mass m is placed on an inclined plane. Okay, let's suppose, so this angle is theta, I am saying. So this angle, the inclined plane angle is theta. So now this mass has mass, like the weight always acts vertically downwards like this mg. But this mg has two components. What are the two components? So as we know, the resolution of vectors, one component will come this side, yes or no? So and the another component will come this side, yes or no? So clear? So the mg has two components. So along the inclined plane we have one component, and perpendicular to that inclined plane we have one more component, yes or no? So here I can say that, so see here, sorry, weight is not, don't write this statement. So weight is equals to mg, but that weight may have the components. So that weight is equals to mg, but it will have components. Okay, so see here, so if it is theta, so shall I say this is 90 degrees? So then this is 90 minus theta, I can say, yes or no? So this is a 90 minus theta, and then so this is again going to be theta. Why? Because this total thing should be 90 degrees. This is the inclined plane and this is the perpendicular. So this total thing should be 90. So if it is 90 minus theta, so this is going to be theta. So then, so mg, so this side theta is there. So mg cos theta. So and this side mg sin theta. So the mg cos theta and mg sin theta. Clear? So these are the components of force. Components of weight, not force, sorry. So the components of weight. So weight is also a kind of force. Understood? Chal. So this is about the weight. Now, so next we have the normal reaction. See, the normal reaction or the normal force, it acts perpendicular to the point of contact. So this exists whenever there is a point of contact. Whenever there is a point of contact, at that point of contact the normal reaction will exist. See here, normal reaction is a contact force between the surface in contact, which is always perpendicular to the surfaces in contact. So this normal force will always be perpendicular to the surface. This will be always perpendicular to surface. See here, I am taking few examples. For example, see here. So this is a body of mass m which is placed on the ground. So then this is a point of contact here. So this is a point of contact. So for this point of contact, so the normal reaction will be perpendicular like this. The normal reaction is equals to, so the normal reaction here, and its weight acts downward. Let it be mg. Yes or no? So the normal reaction is perpendicular to the point of contact and its weight is downwards mg. So see in this case, see in this case, see here, this is the point of contact here, this is a point of contact. So the normal reaction will always be perpendicular to the point of contact. So here in this situation, so the normal is like this. Okay, So here see this one, see this scenario. So here the normal will be so like this. So the normal will always passes through the center. So the normal will always passes through the center. So this is a normal reaction, right? So and then see here. So you can see that there are two bodies which are in contact. This is a point of contact, right? So this is a point of contact. So now the thing is, so the two bodies exerts normal on each other. This body M1 will exert normal on this. This body M1 will exert normal on this, and the equal normal force the M2 exerts on the M1. So this is a normal. This is a normal. Let it be N. So then equal normal force it exerts on the M1. M1 exerts N, then M2 exerts N. Clear? Understanding? So if the point of contact changes, the normal reaction changes. Remember this point. So if point of contact changes, so then normal reaction changes. Then normal reaction changes. So this point is also important. Clear? Understood, guys? Sure. Next you'll understand when we take the questions. Okay. So now, or else I'll give one example for that. For example, if we have three bodies, consider we have three bodies. So this is a block M1, and consider this is a block M2, and consider this is a block M3. So now see here, so this is a first contact, right? So then here at this contact, so the M1, let's suppose it exerted normal N on the M2. So then M2 also will exert N normal N on the M1. Okay, so this is one point of contact. So if the point of contact changes, here the point of contact is changing. Okay, so then here the force acting is N1, the normal force. So then here the M3 will exert force on N1. M2 on the M2, so it exerts N1. So if the point of contact is same, so the normal will be same. If the point of contact changes, the normal reaction changes. So here I am taking N. At this point of contact, this exerts on M2 N. So and this M2 will exert normal reaction N on M1. Yes or no? And similarly here, so the normal reaction changes. Understanding? Everyone? Chalo. So this is also important. Done. So the normal and one more thing. So the normal reaction is not always equals to mg. The normal reaction is not always equals to mg. So what does that mean? So let me take two examples here. For example, so this is a ground or the surface. So consider this is a mass m. So now we have, this is the point of contact. At this point of contact, the normal force acts like this. This is the normal force. What is the other force that is acting on the body? So its own weight, right? Yes. So its own weight, that is mg. So in this particular case, so if the body is in equilibrium, so if the body is in equilibrium, equilibrium means the net force acting on the body is 0. Okay. So if the body is in equilibrium, so then we can say the normal will be balanced by mg. Yes or no? So the n is equals to mg. Then only the body will be in equilibrium. So in this particular situation, so the n is equals to mg. But consider one more scenario. So let's suppose, so this is an inclined plane. So this is angle theta, and consider here we have, so the block of mass m. Okay. So then we have, see here, so the its weight acts downside mg. Yes. Now we have the contact, the point of contact is here. So then the normal reaction will be this side. The normal reaction will always be perpendicular to the surface, point of contact, right? So now if you observe, we have two components of mg. One component along the inclined plane, sine component will come, mg sine theta, and then along the perpendicular we have mg cos theta. So now if you observe, if the body is in vertical equilibrium means, so this force should be balanced by this one. So in that case, so the normal is equals to here mg cos theta. The normal is equals to here mg cos theta. So then the body is in vertical equilibrium. The body is in vertical equilibrium. See, equilibrium can be horizontal equilibrium or vertical equilibrium. If the horizontal forces are equal acting on the body, so then it's in a horizontal equilibrium. Yes or no? So here vertical forces are equal, so there are no horizontal forces. So that's why the body is in equilibrium, I am directly saying. So here horizontal force is there, vertical force is there. So if the body is in vertical equilibrium, so then normal should be balanced by mg cos theta. Yes or no? In this particular case, so the normal is not equals to mg. Normal is not equals to mg. Yes or no? So normal is equals to mg cos theta. So that's what this statement means. So the normal reaction is not always equals to mg. Okay, understood this point? Clear? Chal. So let's move further. This is about the normal reaction. Now done. Next, you can draw the normal for other bodies as well. So if you take some other body, so okay, enough examples I gave. So if you want, consider this one. So let's suppose if there is an object like this, so then draw the normal forces. If they say, so then how do you draw? So here the point of contact is there, here the point of contact is there. Let's suppose here it is normal n1, so here the point of contact changed, so that's why here it's going to be normal n2. So the perpendicular always passes through the center. Normal is a perpendicular line, right? So that's why it passes through the center. Okay, remember the basics. Okay, so this is clear. So now the next type of force is a tension force. So first, the tension force, it's an intermolecular force between atoms of string, so which acts when the string is stretched. So first, where do we observe this tension force? Either in the string or rope or chain. Okay, so in this kind of object we observe the tension force. Okay, whenever a string is stretched or compressed, so in such cases we can observe the tension force. So now the tension force acts on a body in the direction away from the point of contact. So the tension force always acts away from the point of contact. So key point is it always acts away from point of contact. It always acts away from point of contact. Clear? Chal. So if string is massless and frictionless, the tension throughout the string remains constant. So if the string is massless and frictionless, the tension throughout the string remains constant. Okay, I'll give the example so then you'll understand. And then one more thing, if string changes, if the string changes, then tension changes. If the string changes, so then the tension force changes. Clear? So this is one more point. So this is about the tension. Now I'll give you the examples. Understand the examples carefully, guys. See, first, a body is hanged through a string with the support of the string to a fixed support. So this is the string of length L and here is the body of mass M. Now, so as we discussed earlier, so the tension force always acts away from the point of contact. See here, so here this is the string, so here is the point of contact. Point of contact means where object is hanged. So here the object is hanged in this string away from the object. So this side tension will be there. Let's suppose, so this I'll draw here again. So consider this is a fixed support and string and this is the body of mass M. So now the tension acts away from the point of contact. So tension acts away from the point of contact. And then here this fixed support is also a point of contact. Here away from this fixed contact. So if there is no object in between, so the tension throughout that string remains same. Yes or no? So from here to here, there is no object in between there. So that's why the tension throughout the string remains same. Okay, chalo. So now let's understand the second one. So see here. So here is a string. So two masses are connected by a string, and then a force is applied on that. Now the thing is, so this is a point of contact here, and this is a point of contact. So from this point of contact, the tension acts away from the body. The tension acts away from the body, and then from this point of contact, so the tension acts away from this body. As from here to here, the string is same. There are no objects in between. There is no mass attached in between. So that's why the tension throughout this string remains same. From this point of contact away, and from this point of contact away. That's it. Understanding? Sure. So then next, let's take this one. Let's take this one, guys. So if you observe here, so we have, this is called pulley. This is called the simple pulley. So here you can observe that this is a point of contact. Yes or no? So then here the tension acts away from the body. Okay, and again here is the point of contact. So from the pulley away from the point of contact. See, so this pulley we considered it as massless and frictionless. In our syllabus, we consider the pulley as massless and frictionless. Massless and frictionless. So in such cases, we can simply say that, so this is the tension T and this is the tension T. So throughout this string, the tension remains same. Here is the tension T and here is the tension T. So the tension remains same because this is completely one string only. So this pulley is massless, and this pulley is considered as massless and frictionless. So that's why throughout this string the tension remains same and it will be away from the point of contact. So consider this example. So let's take this example. See here. So if you observe, for example, so if I say, so the tension, let it be, so here from the point of contact the tension is T. Yes or no? So and then here the tension is T. Here also from the point of contact away. So this string is same from here to here. So that's why the tension is same. But here to here the tension changes. Why? Because there is mass in between. So here from this point of contact, so the tension will be T1. Let it be. So if it is T, let's consider this as T1. And then from this point of contact T1. So and this pulley is considered as massless and frictionless. So that's why, so the tension T1, T1, T1 again away from the point of contact T1. So again there is no mass in between, again from the point of contact T1. Understanding? So if the string changes or if the mass comes in between, the tension changes. Okay, or else I'll give one more example. Consider. So let's say we have three masses. So this is mass M1, and then this is mass M2, and then this is mass M3. So these three are connected by a string. So here to here string and here to here string. So now let's write the tension forces, guys. See here. So from here to here, let's consider the tension is T away from the point of contact. Okay, and then here throughout this string there is no mass in between, right? So that's why here also the tension T away from the point of contact, away from the point of contact. So now for this string and this string, so there is mass in between. Okay, so that's why the tension changes here. Let it be the tension T1 away from the M2 and away from M3. So here to here there is no mass in between. That's why it's also going to be T1. So that's why whenever the mass comes in between the string, so the tension changes. So this point also you should remember, guys. Understood? Clear? Sure. Next. So this is all about the forces. What are the three forces that we have seen? First, how to draw the weight, and next tension force, next normal reaction. So these three common forces that we have seen, and we have friction force is there, and we have spring force, so that we'll see it in the upcoming classes. Okay, so now how to draw the free body diagram using the normal reaction and the weight of the body, and the if it is attached to a string or connected by a rope, so the tension force also exists. So to draw the free body diagram, so the simple steps, what is, consider the given body as a point mass and draw all forces acting on that body. That's it. So I'll tell you through an example. See, so this is a body of mass m which is placed on the surface. Now, so I am considering this body of mass m as point mass. This is a point mass, so let it be m. So now what are the forces acting on it? We know that whenever there is a point of contact, so there exists the normal, yes, and then so for this body its weight acts downward, mg, yes or no? So now first consider the body as a point mass and represent all the forces acting on it. Here normal is acting upside and mg is acting downside. Normal is acting upside, mg is acting downside. Clear? Understood? Sure. Next. So let's take this example. So here there is no string connected and there is no tension force. Okay. So let's say here this point. First consider this point mass as a point mass. So here there are 2 point of contacts. This is a one point of contact and this is the another point of contact. So I can say, so this is going to be the normal n1, let it be, and then this is going to be the normal n2. And then one more force that acts on this body is mg, its weight. So now we represent it on the point mass. See here, so this side, this is a total mass which is point mass m. So then on this side n1 force acts and this side the n2 force act, right? N1 force this side, n2 force this side, and then so downside the mg force is acting. That's it. Downside the mg force. Clear? So if you need more examples, so consider, let's suppose we have a pulley. So the simple pulley which we call it as Atwood mission. Okay. So this side, so consider we have the block of small m mass and this side we have so the mass of capital M. Consider this is capital M mass. So then see here, so this is a Atwood mission, the simple pulley which is called the Atwood mission. Okay, we'll understand when we do the questions related to pulleys, we'll solve, so there you will understand even better. So now just we are focusing on how to draw the free body diagram, that's it. So see here, first consider the small m body and then consider the capital M body. So small m body, I am considering it as a point mass, and what are the forces acting on it? See here, let's suppose the tension T here. So then here from the pulley the tension away. So here again from the pulley the tension away. See here, there is no mass in between, the tension remains same, right? So and on this M, so the force mg. Okay, so that's why the tension T upside for the small m and its weight mg downside. Its weight mg downside. So and then next, if you draw the free body diagram for the capital M mass, again the tension T upside for that and then its weight mg downside for that. Its weight mg downside for that. This is a free body diagram of this. Or else let's take one more example. Consider the free body diagram of this body. See here, so we have mass m1, mass m2, mass m3, which are connected by the strings like this. Okay, so then so draw the free body diagram of each body. So if I consider the mass m1 body, so let's consider this as a free body point mass m1. So then on the m1 I can say that, so the first the normal force which acts upside n, the normal force, let it be n1 I say. Okay, and its weight acts downside. What is the weight? That is its m1g is the weight. And then right side, what is the force that is acting? Let's suppose here if it is the tension T and this is also the tension T. So this is the tension T. So these are the 3 forces that are acting on the body of mass m1. Now draw the free body diagram for m2. So for m2 I can say that, so this side tension T is acting, yes or no? Left side tension T is acting, and upside, so as a point of contact change, so let's consider the normal m2, and then its weight is going to be m2g, And then so this string and this string, the mass is in between, that's why the compulsory the tension changes. So let it be tension T1, so this also will become tension T1, so that's why right side tension T1. So there are 4 forces acting on the body M2, but only 3 forces on the body M1. Now consider the body M3. So for the M3 body, this is M2 body. Now so consider M3 body, I could see that this side tension T1 is acting, and then upside let's consider the normal M3 because point of contact, and then its weight M3G, and again here also only 3 forces are acting. Understanding how to draw the free body diagram? So now, so next let's take you guys take this as the homework. So the homework question is, consider these are the 3 masses M1, M2 and M3. So draw the free body diagram of M1, M2, M3. So that's a homework for you, and this is the homework 1, and consider the homework 2 is so this is mass M1, M2 and then M3. So draw the FBD of M1, M2, M3. Draw FBD of M1, M2, M3. So here also draw the FBD of M1, M2, M3. So take these 2 questions as homework. Simple thing. So just draw the free body diagram. Understood the concept of free body diagram, everyone? Chalo, so shall we move further? Chalo, so just note it down once. Chalo, see here. So now the next concept, that is the Newton's first law of motion. You already studied it in the grade 9th, that every body continues in the state of rest or in the motion or uniform motion unless and until an external unbalanced force is applied on the body. Yes or no? So then that's the Newton's first law, right? So every body continues in its state of rest or uniform motion along a straight line unless it is compelled by some external unbalanced force, right? So to change its state, unless and until any force acts on the body, if it is in the rest, it continues to be in the rest. So if it is in the uniform motion, it continues to be in the motion. So unless and until some external unbalanced force is applied on the body, right? That's a Newton's first law of motion. So what is that says? So if the net force acting on the body is 0, so if the net force acting on the body is 0, all the forces, the net force means all the forces, so then its acceleration will be equals to 0. So and then it continues to be in the state of rest or in the uniform motion. Uniform motion means speed constant. Acceleration 0 means, shall we simply say, so its velocity or speed is going to be constant. Its velocity is going to be constant. If a body is moving, if there is no force acting on that body, Newton's first law says that that body should move with that same speed. If you throw a body on the ground, if there is no friction on the ground, so then what body should do? So the body should move till infinite distance with the same speed. That's what they are saying. And then let's suppose, so this is a body, okay? So if I don't apply any force on this body, it is in rest initially, so it continues to be in rest. But if I apply any force, this should move, okay? So if once it is in motion, so it should move continuously if there is no forcing act, if there is no force acts on it further, okay? So that's a Newton's first law. So if the net force acting on the body is 0, so then the acceleration, the a net, will be equals to 0. So the a net 0 means the velocity is going to be constant. This is a summary of your Newton's first law. So this statement you already know in the grade 9th level itself. But here, how do we draw the, how do we understand the equations and solve the questions. That's important. See, whenever if the net force is acting on the body is 0 means the F net means, so the force acting in the horizontal direction 0, the force acting in the vertical direction 0, and the force acting in the Z direction is also 0. So this implies that the summation of forces in the X direction 0 and the summation of forces acting in the Y direction 0, and then the summation of forces acting in the Z direction 0. Summation means sigma, sigma Fx 0, sigma Fy 0, sigma Fz 0. So these are the summation of forces acting on the body 0. So then the body is said to be in equilibrium. So which kind of equilibrium? If the F net acting on the body is 0, so that equilibrium is said to be the translational equilibrium. So what is that equilibrium? That's a translational equilibrium, guys. So just understand the basics. Okay. So if the summation of forces in the X direction 0, so the body is said to be in horizontal equilibrium. So summation of forces in Y direction 0 means vertical equilibrium, and Z means, so in the Z direction it is in equilibrium. Understanding? Clear? Sure. Now, so let's move for the question. So just pause the video and try it on your own, what they are saying in the question. 3 blocks with masses m, 2m and 3m, m, 2m and 3m are connected by a string. So they are connected by strings as shown in the figure. After an upward force F applied on the block M, see here, these are connected by string, and on the block M1, on the block M, they are applying the force. So then the masses move upward at constant speed. So all masses move upward at constant speed. If M is moving with v velocity, 2m is also moving with v velocity. So 3m is also moving with v velocity. 3m is also moving with the v velocity. Clear? Understanding? Chalo. So then what is the net force on the block of 2m? See here. If they are all moving with the constant speed, so catch this hint. So if they are all moving with the constant speed v they said. So then shall I say that the net acceleration is 0? If the net acceleration is 0, so then the F net will be equals to 0. So that's why the net force acting on the mass of block 2m, it's going to be 0. Simple logic question. Understood? Chalo. Next. So these are the equilibrium type of questions. Let's understand these questions. See here. So determine the tensions T1 and T2 in the strings. So determine the tensions T1 and T2 in the strings. See here. This is the T1 force. So here is the object. Consider this as root 3 kg object. This is a root 3 kg object, and then so we have so 2 forces acting on this body. So one is tension T1 and this side tension T2. So now see, first what I will do is I will draw the components of force. What are the components of force? See here. So downside root 3, its mass into g. Its mass into g will act downside, and then so this T1 will have 2 components. Right side the T1 cos 60 degrees, and then so this upside T1 sin 60 degrees. Yes or no? If this angle is 60, so as 60 is this side, cos component of 60 will come this side, and then sin component will be this side. So now if you draw the free body diagram of that, so this is a root 3 kg body. Downside the root 3g is acting down, and right side T1 cos 60 degrees is acting right side, and then upside so T1 sin 60 degrees acting upside, and then left side so it is T2 force is acting. That's it. T2 force is acting. So now simply if the body is in equilibrium, consider the body is in equilibrium. So if the body is in equilibrium, so shall we say the summation of forces in the x direction should be 0, and then the summation of forces in the y direction should be 0. So in the x direction what do we have? T1 cos 60 degrees should be balanced by, so this should be balanced by T2. Yes or no? And then So this one T1 sin 60 degrees should be balanced by root 3g. Root 3g. So now see here. So T1 cos 60 degrees, which is 1 by 2, which is equals to T2. So from here what I am doing is, let's first find what is T1 value. T1 into sin 60. This is going to be root 3 by 2 is equals to root 3 into g. So here root 3 cancel. So T1 is equals to 20 newtons. Yes or no? 2 into g. So let's take g as 10. So T1 is equals to 20 newtons. So then substitute the T1 here. So then we get 20 into half is equals to T2. From here the T2 is equals to 20 by 2. So the 10 newtons. T2 is 10 newtons and T1 is 20 newtons. Yes or no? Clear? 20, 10 is the correct answer. Done? Chalo, simple question. Let's move for the next question. What's the question says? First understand the question and draw the free body diagram. So the pulleys and strings shown in the figure are smooth and of negligible mass. For the system to remain in equilibrium, so the angle theta should be, so the system should be in equilibrium. Okay. So first draw the free body diagram here, guys. So this is the root 2m. So for this root 2m into its g will be the weight. Root 2m into g will be the weight. And then so see here, this is a mass m. Consider, let's suppose its weight acts mg downside, and then let the tension T. So and see here, there is no mass in between, the tension T here. So see here, this is pulley, massless pulley. So here the tension T. So and again here see here. So again here the tension T. See, the mass is not connected in between. The mass is connected like this. So in this case, if the tension is T here, here also the tension will be T. So if the tension is T here, so here also tension T. So but if the mass connected in between like this, so then the tension here and tension here will change. Understand the difference? Okay. So in this particular situation, so the tension remains same. Where? So here if it is the tension T, and here also the tension T will act. Yes or no? So and then again away from the pulley T, and again away from the pulley T. So and here again here T, so and here mg. Yes. So now see, they said, so for the system to remain in equilibrium, so first I'll consider this portion. Okay. So at the root 2m is a point mass here. For that root 2 mg is acting downside. Root 2 mg is acting downside. And if you observe, shall I say that this T will have two components. This side the T sin theta, and then this side the T sin theta. Yes or no? If it is theta, so this is also theta. So then this side the component that comes is T cos theta, and then this side also the component that comes is T cos theta. Yes or no? So if theta is this side, so the T component will come this side, which is T cos theta. This side T sin theta. So this T sin theta, this T sin theta gets cancelled. Yes or no? So you can see here. So this side T sin theta, and then this side also T sin theta. So they both get cancelled. They both get cancelled. And then so this is root 2 mg, and then this upside it's going to be 2t cos theta. This is going to be 2t cos theta. Understanding? So now if you observe, so these two will directly get cancelled. So if consider the body is in vertical equilibrium, so sigma y is equals to 0. So then 2t cos theta will be equals to root 2 mg. 2t cos theta will be equals to root 2 mg. So then shall I say that in place of t, shall we consider t is equals to mg here, either from here or here. So t is balanced by mg, right? So that's why in place of t I am writing mg into cos theta is equals to root 2 m into g. So here mg cancel. So from here the cos theta is equals to root 2 by 2. So here root 2 by, in place of 2 I am writing root 2 into root 2. So root 2 cancel, which is 1 by root 2. So therefore the cos theta is equals to 1 by root 2, So from here theta is equals to 45 degrees. So the theta is equals to 45 degrees is the correct answer. Understood guys? Clear everyone? Sure. Then next. So let's take the next question. So just try it on your own. See here what's the question says. In the arrangement shown in the figure, so what be the mass of the block A so that the system remains at rest? So rest means equilibrium, neglect friction and mass of the string. See here. So first this is a 2 kg body and here block A is attached and this is the 2 kg. So what should be the mass of this body A, block A, so that the system remains in the equilibrium? Okay. First draw the free body diagram. Let its mass be M. So that here mg will act downside and then let the tension be T here. So and again from the pulley the tension will be T here. Again from here the tension will be T and again from here the tension is T. See here, this is a string. In between the string the mass came. So that's why the tension changes here. So let it be T1. Let it be T1 is the tension. So I'll draw the diagram again so that you will understand. So that some was not clear. So see draw the diagram again here. So here is a 2 kg block, right? So then here is the pulley attached and then this side the block of mass A, let it be M, and then this side again we have the pulley and then this side, so it's a 2 kg block. Okay, so then see here this is going to be the mass mg downside, right? And this side the tension T. So and here also the tension T and here also the tension T, but here the tension changes. This is tension T1 and this string is total same. So here it is going to be tension T1. Yes or no? So now let's consider this portion. So the 2 kg block portion. So draw the free body diagram for the 2 kg block portion. So what I am doing is, let's take this as horizontally, like consider this total thing as x plane. I am taking it as horizontally. So on the 2 kg block, so this side tension T is acting. So this side tension T is acting and left side tension T1 is acting. Along with that, so along the inclined plane, so this angle is given as 30 degrees. See here. So this angle is given as 30 degrees. So then along the inclined plane, so its weight is going to be basically 2g. Along the inclined plane we get 2g sin 30. Understand this one. When the mass m is there on the inclined plane, where is that? When the mass m is there on the inclined plane, so the mg sin theta will come along the inclined plane. Yes or no? So then in this particular situation also here, where is it? So in this particular situation, so you could see that 2 and 2g will act downside and along the inclined plane 2g sin 30 will come. So that means along the T1, this side T1, right? Yeah. So along the T1, so this side 2g sin 30 will come. 2g sin 30 degrees. So simply I can say that T1 plus 2g sin 30 is equals to, so T. Yes or no? So now I can say that T1 is equals to 2g. T1 is equals to 2g plus this one is what? 2g sin 30 half. So what is T? T is balanced by mg. T is balanced by mg. See here, T is balanced by mg and T1 is balanced by 2g. Basic things, right? So from here, T in place of T I am writing mg. Now we need this m. So see here, 2 cancel. So 2g plus g. So which is 3g is equals to mg. So here g cancel. So the m should be 3 kg. So the mass of block A should be equals to 3 kg. Option 4. So that the whole system will remain in rest or equilibrium. Understood? Clear this point, everyone? Chalo, next. So and Lami's theorem, already we discussed it in the vectors. So whenever 3 forces are acting at a point, so if the forces acting at a point, see here at this point force F1 is acting this side and force F2 is acting this side and force F3 is acting this side. So if this angle is alpha, this angle is gamma, this angle is beta. So then what we say? F1 opposite of that, F1 by the sine alpha is equals to F2 opposite of that. So opposite angle sine beta, and then F3 and opposite angle which is sine gamma. So this is a Lami's theorem. When three forces are concurrent which are acting at the same point and making the angles alpha, beta, gamma, so then the relation between those forces and angles is given by the Lami's theorem. So this will be useful when three forces are acting on a body at the same point. Okay, so let's see the question so that you will understand its application. So let's try to solve this question, guys. Let's try to solve this question, the last question for today's session. Here, a block of mass 10 kg is suspended by 3 strings. Okay, so as shown in the figure, so the tension T2 is, so they are asking tension T2. So see here, a mass of 10 kg suspended by 3 strings. So see here, here is the 10 kg block. So this is the 10 kg block. So and it is suspended by 3 strings. So downside tension 1, this side tension 2. So like this is a diagram. We can say that this side one string tension 3, and this side tension 1, and this side the tension 2, and this is a 10 kg block. So now you have to add, find what is T2. So you have to find what is T2. So the simple logic, you can find T2 very easily. You can find T2 very easily, yes or no? So how? So first this is 60, this is 30. This angle is going to be 90 degrees, guys. This angle is going to be 90 degrees. So then can we find all the angles here? So what are all the angles? You can observe that. So first, if this is 90, so obviously this is 90 and this is also 90, the perpendicular. Yes or no? This is 90, this is 90. So and then what is this angle? What should be this angle? Tell me. What should be this angle? If it is 60, so this angle is to be 60. If this is 30, so this angle to be 30 degrees, because this line and this line are parallel. So then you observe now what are the angles that we required. What is this total angle? This total angle, I could see that 90 plus 60, yes or no? 90 plus 60, 150. This is the gamma. And then what is this total angle? 120 degrees. And then what is this angle? 90 degrees. Yes or no? Between T2 and T3, this angle is 90 degrees. Yes, total we have got alpha, like alpha, we have got beta. Consider this as beta, consider this as gamma. So then what you can do, simply T1 by sine 90 is equals to T2 by sine 120 is equals to T3 by sine 150. T3 by sine 150 degrees. That's it. So T1 by Lami's theorem I am using. T1 by sine 90, T2 by sine 120, and then T3 by sine 150. So here you could see that they asked for T2. So just relate these two. So if you relate these two, so T1 by sine 90 is 1. So T1 is equals to T2 by sine of 90 plus 30. We can write this one. Sine of 90 plus 30. So what is sine of 90 plus 30? Cos 30. Sine 90 plus theta, which is in the second quadrant. In the second quadrant, sine is positive. So that's why. So I can write this as T1 is equals to T2 by cos 30 from here. So the T2 is equals to T1 cos 30. T1 cos 30. So what is T1? T1 is equals to 10G. So 10G, yes or no? From here you could see. So T1 is balanced by its weight 10G. So T1 is equals to 10G. So 10 into G into what is cos 30? Root 3 by 2. So this is going to be 5. So which is 50 root 3. So this is going to be, so 5 into 10. So 50 root 3 newtons. Option D4 is the correct one. Clear? So simply I use the Lami's theorem. Or else if you want, you can follow the component method also. The resolution method also you can follow. Your wish. Okay, understanding? So chalo guys. So let's see, that's it for today. So just we learned basics today. How to draw the free body diagram and how to apply the equilibrium conditions using the Newton's first law of motion. And then what are the different types of forces that acts on the body and how do we represent them in the free body diagram. So in the second class, that is tomorrow's class, we are going to start with the Newton's second law, which is very very important. So then we'll understand what is momentum, what is impulse, and what is the relation between momentum and change in impulse. And whatever the terms that we come across, any new terms that we come across in today's session, only force, right? So because wherever we come across the new terms, you have to write the dimensional formula, guys. Don't forget that. Okay, so even if I forget, so what you do is you write the, if the new terms comes, let's suppose work came, or let's suppose some other term come, momentum has come, some impulse has come, you have to write the dimensional formula, because we have already covered the dimension, units and dimensions chapter. So 4 lectures I have dealt, right? So that you have to do yourself. Clear? So we'll meet in the next lecture, that is tomorrow. Till then, keep studying. All the very best, students. Bye.